Good afternoon, one and all. I'm happy to welcome you to this afternoon seminar, part of the Modern History of Mathematics program at the Ivy Newton Institute this term. We have with us this afternoon Christopher Hollings from the University of Oxford, who's going to tell us about 19th and 20th century historiography of ancient Egyptian mathematics. Over to you.
Thank you. And thank you everybody for coming. So I sort of figured that since I'm not really otherwise speaking as part of this program, I might offer a seminar. And it sort of ended up being at the real sort of tail end of the program. So with it being a Friday afternoon, at least for the people in the room, I thought I'd just have a sort of gentle meander through a project that I've been working on for a few years with Richard Parkinson, who is a professor of Egyptology in Oxford. And a few papers have come out of this so far. So if anybody wants to know any more specifics of any of the things I'm going to sort of talk about in survey, I'm quite happy to sort of point you in the right direction. You'll have noticed that I've squeezed in the word modern into the title simply by way of justifying or trying to justify talking about ancient Egyptian mathematics in a program called Modern History of Mathematics. So it's going to be very much more modern historiography than ancient history in a way. So we've been working on this project for a few years, as I say, and it's something that started from a couple of letters that turned up in a library in Oxford, and it just sort of spiraled outwards from there. And we often frame the project around the question, how do we know what we know about ancient Egyptian mathematics? And so it's a story about the reconstruction of that knowledge in the 19th century as part of the wider reconstruction of the languages and scripts of ancient Egypt. And we're particularly interested in the different attitudes that go into that rediscovery of that knowledge. So, you know, the mathematicians say one thing, the Egyptologists say another, the historians of mathematics say something else entirely. So we're interested in that sort of patchwork of attitudes that go into this knowledge. So just to start with, if I can find the right button. Nope, not that one. That one. Oh, hasn't come out fantastically well, but just a bit of basic geography to get us started. So this is Egypt with various labels relating to ancient Egypt. So very much a sort of long, narrow country concentrated around the Nile, which is relevant to the story I'm going to tell. Just one place to point out here is Thebes, so ancient capital of Upper Egypt. I'm pointing that out because that's going to come up again in a short while. And also, let's have a nice timeline to start things off. So there's a lot going on there, but just to give you a sort of basic idea that I still find it mind-boggling, the sort of spans of time that are involved in talking about this civilization. And even what is even more mind-boggling is the extent of the continuity that stretches through these different periods in comparison to sort of the frenetic modern age that we live in. But broadly speaking, the main part of ancient Egyptian history is divided into the three kingdoms, so Old Kingdom, Middle Kingdom, New Kingdom. So pyramids are from early Old Kingdom, and in the Old Kingdom we have scattered evidence of numeration and, you know, bits and pieces, but nothing very substantial by way of evidence of mathematics. More comes in the Middle Kingdom. There's still not a vast amount of stuff. So what I've often said is you can't quite count the ancient Egyptian mathematical sources on one hand, but two hands is plenty. So there's really not a lot out there. But as for the Middle Kingdom, if you think about the things that you may possibly have read about ancient Egyptian mathematics in the general histories of mathematics, you're probably thinking of things that come from the Middle Kingdom. So this is where a lot of the evidence comes from. And then as we move into later periods, there is more evidence of mathematics, but strangely, that's been much less studied. over the decades. And that's partly to do with certain biases that are built into the way that Egyptology was professionalized in the 19th century, which it tended to privilege a sort of an idea of a classical age in the Middle Kingdom, and so later periods have received slightly less attention, or at least the mathematics has anyway. So what I'm going to talk about really sort of centers around people studying the mathematics from the Middle Kingdom. What I should probably also do before I start talking about the question of how do we know what we know, I should maybe address what do we know. I had several slides at this point and then realized the talk was going to be well over an hour, so I took them out again. But basically, we're talking about a very well developed system of arithmetic, particularly fractional arithmetic. There's a sort of decimal system in place. The thing that people often know is that mostly only unit fractions are used, and there's the systems of reference tables for converting between different types of fractions. And there's some geometry, but in many ways the geometry is arithmetic. We want to find this area, so here are some numbers, and you do this with the numbers to get another number. So essentially, it's sort of arithmetic, and there's nothing like the sort of things you find in Euclid, for example, which again is a point that will come up again very shortly. And this mathematics is used to do things like calculating, well, as I've already mentioned, areas and volumes, distribution of rations, this kind of thing. And in many places, or in some places, there's a sort of sense of slight arithmetical playfulness with the numbers. So, there's an ongoing question about, is ancient Egyptian mathematics inherently practical? And the answer is perhaps no, not entirely, because some of the numbers that are employed, sometimes you think, well, they're not plausible from a practical point of view. That's somebody playing with numbers, probably. Okay, so on to the question of how we know what we know. So we have to go to the place where people have often gone to when they want to learn about ancient Egypt, and we start with Herodotus. So people outside Egypt writing about Egypt essentially starts with Herodotus. He's traveling there in the 5th century BC. He's writing down what he sees. He's writing down what people tell him. He seems to write things down quite accurately, but uncritically. So some of the things that you find maybe not necessarily, maybe don't necessarily stand up to scrutiny. And one of the things he mentions in relation to mathematics is he tells the story that has been related to him of a pharaoh. Sesostris is the name that's often used, but he's a sort of semi-mythical figure. But so a pharaoh who divides up the land, gives people parcels of land, and each year the Nile floods, and the markers marking out people's lands are obliterated, so they have to be marked out afresh every year. And out of this need for surveying, geometry is born. So this is what Herodotus tells us. And we can sort of question whether people with the engineering skills that they did have would actually put themselves in a position where they had to do this every year. But anyway, this is the story that Herodotus relates. And so from this, we get what are essentially the two basic facts, in inverted commas, about ancient Egyptian mathematics that are then passed down for the next 2,000 years without any further details attached to them. The idea that geometry is invented in ancient Egypt because of the needs of surveying. And secondly, fitting in very much with the ancient Greek view of Egypt as the fountain of all wisdom, knowledge of geometry passes from Egypt into Greece. So these are the two things that Herodotus asserts, and that's it. In terms of details of how the mathematics works, there's nothing coming from Herodotus. And there's a few embellishments over the following centuries. So reference, for example, to the so-called harpadatoni. Sorry, I always get that word wrong. The so-called rope stretchers, who are sort of supposedly marking out temple boundaries with knotted ropes and so on. But essentially, this is it. And the fact that by the time you get to the middle of the first millennium, AD or CE, all knowledge of ancient Egyptian languages and scripts has gone through various mechanisms. So this is the only thing that people have left to draw upon, this very vague idea coming from Herodotus. And it remains even in sort of medieval Islamic Egypt. There are people there with mathematical expertise. There are people there with an interest in the monuments that are littering the landscape. So there's a lot of measuring and surveying going on and speculation about why these things were built and how they were built, but nobody can read anything. And so sort of in sort of the Middle Ages, the only knowledge that people have in Egypt of ancient Egyptian mathematics is through Arabic translation of Herodotus. So still, it's just this sort of basic idea. I should mention one thing that I'm sort of deliberately leaving out of this story is the sort of the slightly more mystical aspect, so the Hermetic tradition and so on. That's partly from a lack of knowledge on my part. This is something on my to-do list to learn more about. But also I find it slightly difficult at the moment to figure out how to actually fit that into this story. So that's something I will have to look at in the future. Okay, so skipping quite lightly down the centuries, coming to the mid-18th century, we have Jean-Étienne Montoucla attempting to write the first reasonably comprehensive history of mathematics. And there's a great contrast here between what he writes and what you find on ancient Egypt in modern books on the history of mathematics, where you typically will have a whole chapter, say, on Egypt. Montoucla has a paragraph in which essentially he's just telling you what Herodotus said. So it's still Herodotus. Things look slightly more promising a few decades on when we get to the sort of the monumental description of Egypt, the sort of multi-volume publication that comes out of Napoleon's forays into North Africa. And in there we find an article on Egyptian systems of measure by Edmé Joumard, who was an engineer who went to Egypt. And it's quite substantial. I think it's a couple of hundred pages long. And so you think, okay, well, here is somehow or other, somebody has gained some knowledge of ancient Egyptian mathematics and systems of measure. And actually, no, he hasn't really. It's just a very, very comprehensive survey of everything that every classical writer has ever said about these topics. And it doesn't really add all that much to the story from Herodotus, apart from perhaps the discussion of various sort of biblical measures and so on that are sort of built into the story. So I suggested that this story about having to mark out lands every year is not, you know, we can question the plausibility of that. And I'm in pretty good company, I would say, in questioning that. So if we look to Augustus de Morgan, so a very keen historian of mathematics and somebody who's always quite good for a soundbite. So around 1830, he's writing for the Penny Cyclopedia, so a serialized reference work. He writes most of the mathematical entries, and he in particular writes the entry on geometry. And he begins that entry with a short, well, not that short, history of geometry. And in this history, he refers to the fact that there seems to have become a stock history of the rise of geometry, that the Egyptians, having their landmarks nearly destroyed by the rise of the Nile, were obliged to invent an art of land surveying in order to preserve the memory of the bounds of property, out of which art geometry arose. And then he goes on to sort of muse on the theme that if we are to call something history, then we have to have some evidence for it. And for this, we have no evidence beyond Herodotus. So he's somewhat skeptical. But what De Morgan probably knows at this stage is that we're sort of on the cusp of a change, because things are starting to happen when it comes to reading ancient Egyptian sources. So on the left, we have Champollion, Jean-François Champollion, working in France on ancient Egyptian language. And on the right, Thomas Young, similarly working in Britain. And together they're the people who make the first major strides into reconstructing various different phases of ancient Egyptian language and the different scripts that were used over time. And so this is not this sort of great sudden ability to read ancient Egyptian texts. This decipherment process is something that sort of unfolds slowly over the 19th century, but they're making the first steps sort of around 1820 and decades either side. And certainly they've identified numerals in the scripts quite early on. This is something that I think when you look at other contexts, it happens quite quickly. I know in the case of Linear B, in the Minoan setting, the numerals were one of the first ways that people found into the script. And there seems to be a slight controversy over who first identified the numerals. So Thomas Young makes a claim, but also Jomard, whose article we had on the slide a couple of minutes ago, also makes a claim. And I don't know the answer to this. It's something that I might try and look into at some point. So we have knowledge of numerals, certainly. Knowledge of mathematics more widely still isn't there, simply because the sources aren't there. So the numerals are coming out of lists of workmen on a project with just numbers attached to them and that kind of thing. So for actual sources on what ancient Egyptian mathematics, what arithmetic, what the processes of mathematics looked like, we have to skip forward another couple of decades to the work or sort of things surrounding this man. So this is Alexander Henry Rind, who is a Scottish archaeologist, in fact, a pioneering archaeologist who promoted an idea of a scientific archaeology, of a kind where you actually record things, where you find them and so on. It's sort of kind of not the way that people had worked up to this point. So he works on excavations in Scotland for a time, but he has poor health, and he is advised, as so many people were, to travel to somewhere with a dry climate where he might recover. So he goes to Egypt. And it has to be said, this did not, as a strategy, this did not work well for him, because he died in 1863, aged just 30. But before that happened, he'd amassed a collection of various objects, that some of which he'd excavated, some of which he bought from antiquities dealers in Egypt. And the bulk of his collection is now in Edinburgh, in the National Museum of Scotland. But one or two things did find their way to the British Library, the British Museum. And this is one of them. So you've probably heard of it. It's the Rind Mathematical Papyrus, which takes its name from him. Quite why this ended up in the British Museum, separate from all his other stuff, I'm not clear about. I think there's some archive work to be done in the British Museum to figure that out, because he seems to have had some contact with Samuel Birch, who was one of the keepers there. So perhaps Rind bought this to order from the British Museum, possibly. I mean, that's something that needs to be figured out. But certainly he didn't excavate this. He bought it from an antiquities dealer in Luxor, so ancient Thebes, which is why I pointed out on the map at the beginning. It's very well preserved, so it probably came out of a tomb in the nearby Theban necropolis, but we don't know for certain where it actually came from. So on the screen here, it's much bigger than it actually is in real life. It's about 30 centimeters tall, and the whole thing is about 5 meters in length, but it is broken into two pieces. Probably the person who got it out of the tomb tore it in half in order to double the price. The two halves do survive reasonably well in the museum. And so you can see just from this section that I've got on the slide that you might suspect there's something mathematical going on here, and certainly people did. So there's early correspondence about this with Samuel Birch at the British Museum, referring to this as a geometric papyrus. So there's some excitement that may actually learn something about ancient Egyptian mathematics from this source. And this gradually happens. So a decade on, The first detailed treatment and translation of the content of the papyrus comes from August Eisenlohr, who is a German Egyptologist. And actually, this work was sort of heavily updated, as we'll see, but actually it's quite a remarkable text that he manages to put together, because he's working at a time when the understanding of the underlying language, namely Middle Egyptian, is still not there. I mean, people can understand it to an extent, but it's an ongoing project to reconstruct this language. So the fact that he's able to make any sense of what's going on in this mathematical papyrus is quite remarkable. And in part, it's because he often follows the mathematics. So if he can't quite make sense of the text, he says, well, what should make mathematical sense based on the numerals that we can see on the page? And that usually works. I mean, there are a few places where it leads him astray and people later on have corrected him, but it's not too bad a strategy in his case. And so this is where people are getting their first detailed glimpse of what ancient Egyptian mathematics looked from. So that system of fractional arithmetic that I mentioned early on, the different methods that were available for calculating certain areas, say, this is where people start to see this for the first time. And it gets digested for mathematicians. And when I say digested, I basically mean all the Egyptology is taken away. So any concern about philology and arguments over translation gets swept aside completely, and we just focus on the mathematics. And one of the big places where this happens, first of all, is in Moritz Cantor's Geschichte der Mathematik, where he just presents the mathematics that is in the papyrus. And so for many mathematicians, this is their first glimpse of what ancient Egyptian mathematics looks like. And they're actually a bit disappointed in it in some ways, because it's arithmetic. It's fairly elementary arithmetic. I think that there are interesting things in there, but if you're looking for something more sophisticated, you won't find it. I think mathematicians are turning excitedly to this at this point, looking perhaps for some sort of proto-Euclid or something along those lines, and that's just not what they're finding. So there's a certain amount of disappointment, and yet the fact that this exists enables them to push the detailed history of the discipline back an extra 1,000 years. And so a theme that recurs after this is very much the idea of sort of mathematicians. They're not so interested in the mathematics, but they like the fact that it's there, that it's part of this story, that you can put it on a timeline way over here in order to take pride in the antiquity of the discipline. But what this also means, of course, is that the mathematics gets increasingly divorced from its original context. So divorced certainly from any kind of Egyptian cultural context to some extent, and separated from the original languages and the form that it took. And mathematicians just don't see that anymore. They see these digested versions. And they sort of try to force this ancient mathematics into a more modern mold. And this is a page, I think it's from one of Florian Cajori's books. I've forgotten where I got it from, which contains this abomination, which is, a sort of a string of hieroglyphs put together as if it were a modern equation, as we will write it with here's the equation underneath. And this bears no resemblance whatsoever to anything that an Egyptian scribe would ever have written down. Because in particular, it wouldn't have been in hieroglyphs. It would have been in a cursive hieratic script, which is what the Rhine papyrus is in. Hieroglyphs are good for temple inscriptions, not so good for handwriting. So certainly this is not what you would see. But this is how these ideas get incorporated into books on the history of mathematics at the end of the 19th century. And there's a real flurry of interest in this topic by mathematicians. It's short-lived because of the disappointment that I mentioned, and it sort of dies away somewhat. And these ideas just sit there at the beginning of the general histories of mathematics, possibly alongside the details of Mesopotamian mathematics that are just starting to emerge at this time. but always before Greece, because we have to get to Greece in order to get to the proper mathematics, which is the sort of the attitude that persists at the time. So that's the mathematicians, but the Egyptologists are still continuing to look at this material, not so much from an interest in mathematics, but from ongoing efforts to sort of improve their understanding of the language. It's sort of an acknowledged fact around this time that Egyptian philology is so dynamic as a subject that almost as soon as you publish an edition of a text, it will be out of date. And this is exactly what happens with Eisenlohr's text. So by the end of the 19th century, there's very definitely a sense that we need a new edition of this papyrus. Again, the Egyptologists perhaps not so interested in the mathematics as such, but the papyrus is actually a very good example of the language of the period, which I realized I didn't mention. So this is about 1500 BC is the Rhind papyrus. So from what's called the Second Intermediate Period, but it claims to be a copy of a text written 200 years earlier, which places it right at the end of the Middle Kingdom. So right in that kind of the period where we have other evidence from. So there are sort of piecemeal corrections to Eisenlohr's text at the end of the 19th century, but for an entirely new and full edition of the papyrus, we have to go to 1923 to an edition produced by this man. So this is one of my favorite characters in this work. I find him really interesting figure. So this is Thomas Eric Peat, who is an Egyptologist, but someone who'd first gone to university at the beginning of the 20th century and studied a year of mathematics, and then decided he didn't want to do that and became a classicist. That led him into an archaeological career, but by the beginning of the 1920s, he's shifting away from excavation and he's reinventing himself as a philologist. And he produces editions of various different ancient Egyptian texts, and the Rhind papyrus is one of them. And I think the Egyptologists have spent much of the 20th century saying, oh, well, Pete studied mathematics at university, that's why he was able to do this. I think that's not quite true, because anybody who'd done mathematics at school could understand the mathematics of the Rhind papyrus. It's really not that complicated, but it does seem to signal that he had an interest of some kind in mathematics, which most Egyptologists weren't bothered about. The attitude seemed to be that they're quite happy that somebody is looking at ancient Egyptian mathematics. They're just glad it's not them. So it's sort of adding into the picture from the sides, if you like. So this edition of the Rhind papyrus quickly becomes the standard edition for Egyptologists. It sort of supersedes Eisenlohr's. Something I'm not going to talk about for lack of time is that in the late 1920s, you get another edition of the Rhind papyrus by a man called Arnold Buffum Chase. And for reasons I won't go into, that sort of becomes the mathematician's edition of the Rhind papyrus, whereas this, as I say, is the Egyptologist version. And it seems the appearance of this in 1923 reignites a general interest in ancient Egyptian mathematics. It's giving you a sort of fresher view. Peat is able to provide a sort of a sort of better cultural background to the papyrus, simply because he has access to much more recent scholarship than Eisenlohr had. So it gives you a really nice picture of where mathematics sat in wider Egyptian culture. So it reignites interest in ancient Egyptian mathematics among Egyptologists a little bit, mathematicians a lot. But also in sort of a new type of scholar that seems to have emerged at this point. People who are increasingly becoming professional historians of mathematics, and in particular people who are interested in actually bothering to learn the ancient languages that you need to know in order to do the study. And so the main person I have in mind when I say this is Otto Neugebauer. So he's begins his university studies as studying mathematics and physics, but of course he moves into Egyptology, and so he's studying with some very prominent Egyptologists in Göttingen, and his very first publication in the early 1920s is a review of Pete's edition of the Rhine Papyrus. And he seems to have then got into correspondence with Pete, and Pete's edition then becomes the main source that Neugebauer has when he's writing his PhD dissertation in Göttingen, which he completed in 1926, and it's on ancient Egyptian fractional reckoning. So he's in contact with Pete, and something I will come to very shortly is that we do actually have quite a nice view of what Pete thought of Neugebauer's work, because Pete is then writing to other people about Neugebauer and providing his opinion, which generally is positive, but not unqualified. And Neugebauer and various other people like him around this time, so Kurt Vogel slightly later in the 1920s, are bringing a particular attitude towards the study of ancient mathematics. It's one that sort of has been criticized much later on. It's a kind of partly a sort of code-breaking kind of attitude that really just focuses on the mathematics, doesn't worry about what's going on around the mathematics. And Neugebauer does seem to, in particular, display a kind of what you might say is his Göttingen background in mathematics in what he does, in that he looks at the ancient mathematics and he's forever looking for underlying principles or overarching principles, if you like, depending on which way you want to do it. And so you can see this in particular in this table. I'm not going to go into huge detail about what's going on here, but this is a centerfold of one of the letters that he sent to Pete, and it's an elaboration of some of the things he includes in his dissertation. And so what's going on here is, so in each of these blocks is a problem from the Rhine Papyrus. And what Eisenlohr had done in his edition is he helpfully numbered all the problems. And so we've got this canonical numbering to work with. So this is problem 11, and I won't go into what's going on there because it's a not hugely complicated, but slightly involved method for doing certain calculations. So problem 11, problem 12, problem 14, and so on. And what Neugebauer is doing in this table is he's looking for the underlying systematization of these problems. He's saying this is how this collection of problems was constructed. However, in order to do that, you may notice that there's a claim that problem 12 derives from problem 11 and problem 14 derives from problem 12. Problem 13 is down here because it doesn't fit between 12 and 14. So in order to do this systematization, he's having to reorder the problems in the papyrus, first of all. And then you may also notice that problem 11b is entirely enclosed in square brackets, and that's because there isn't a problem 11b in the papyrus. So he's got this sort of grand scheme for how all of these problems must fit together, but in order to make it work, he has to reorder them and interpolate entirely new problems. The mathematics is very definitely taking the lead here, and as I say, it's the kind of approach to ancient mathematics that has been criticized more recently for being too much like an attempt at code breaking. But he's working like a mathematician when he does this. It's not that he's sort of working in a vacuum. He's thinking very much like a mathematician would think in how to approach this material. And he also is quite happy to enter into this kind of speculation as well. This is very clear from his writings, and he is it stands in stark contrast to Pete in this. Pete is extremely cautious in his writings. I have to say, sometimes frustratingly so. But he does not like to go beyond what is written on the page, at all. He doesn't like to do this kind of speculation. And you also see similar things going on in reference to this table, and it might be a table that people are vaguely familiar with. So this is a table that takes up most of the recto of the Rhine Papyrus. And as I think I mentioned earlier, at least notationally, Egyptian scribes only used unit fractions, or almost only used unit fractions, which causes you a problem if you want to express something like 2/5. You can't write that down. There is no notation for that, so it has to be expressed in terms of unit fractions, and it's 1/3 plus 15th. And so this table on the papyrus is a reference table for telling you how to do this. So there's various different ways of looking at this. It's often described as a table of duplications of unit fractions with odd denominators, because it stretches all the way from 2/3 down to 2/101. And the work of Neugebauer and others in the 1920s says, well, okay, there has to be some kind of underlying principles to how this table is constructed, because these representations of these different fractions in terms of unit fractions are not unique. So they have to be able to make a choice, and what are the principles on which they're basing this table. And so this is a large part of what Neugebauer's dissertation is about. And the table I showed you on the last slide is a part of his attempt to systematize this. And he's certainly not alone. There's a lot of interest in people and argument with people trying to find these rules in the 1920s, and it goes on to this day. Pete's view is a slightly more pragmatic one, arguably slightly less interesting one, but probably more accurate, which is that this is probably a table that is just accumulated over many centuries of compilation, which would be consistent with the way that other texts were compiled in this period. So it's not an exciting explanation, which is probably why people like Neugebauer are not keen to go with it. And of course, this also fits with what you may know about the way that Neugebauer and others are sort of working in this idea of this Platonic view of mathematics, that it's the same mathematics as the mathematics that we study. So it's okay for us to make this identification and to rewrite things in certain terms. And it's one of the reasons he's been criticized, but I would defend him on many counts. I think he's by no means the culprit that he has been painted as sometimes. I think the criticism has been a bit unfair. But anyway, in all this, certainly mathematics is at the center. This is what he's interested in. He's not interested in the wider Egyptology, and that's why he eventually moves on. So by the time we get into the early 1930s, he's not really doing Egyptian mathematics anymore. He's moved on to Mesopotamia because it's mathematically more interesting as far as he's concerned. But anyway, so sticking in the 1920s, this is the kind of thing that's going on. There's a sort of whole load of activity around problems like this from sort of mathematically inclined readers. So the natural question is, what are the Egyptologists thinking about this? And this is where we can tap into what Pete writes to Alan Gardner. So Gardner was a sort of very big figure in British Egyptology in the first half of the 20th century, pretty much controlled British Egyptology. And he was Pete's mentor. So we find these very candid letters that he writes to Gardner. So he talks about Neugebauer's dissertation. So he notes that he's had correspondence with Neugebauer. Frankly, I don't even now fully follow his demonstration, though I think he's right and shall doubtless agree after I've read him more carefully. I'm inclined to think he exaggerates the additive character of Egyptian mathematics. So this is the other point in Neugebauer's dissertation. He makes the argument that there is no concept of multiplication, or no general concept of multiplication in ancient Egyptian mathematics. You have doubling, you have multiplying by 10, but those are conceived as entirely separate operations rather than instances of a more general idea. And so that essentially the whole mathematical scheme, the whole arithmetical scheme is completely additive. This is something that he argues there. And he argues it very strongly. But Pete thinks he's inclined to exaggerate that. And so that's another theme that runs through. So Neugebauer and others are very certain of their conclusions, but Pete, ever the cautious Egyptologist, is never quite happy with the certainty with which people put their ideas across. But still, he's very happy that this has served to reopen the study of ancient Egyptian mathematics. He's happy to see this being studied. But just on this point about certainty, so Neugebauer sent a copy of his dissertation to Pete, and that survives in a library in Oxford with Pete's annotations. And if you have a look through, if you look at the book, it's a lot more legible than that. So this is a passage where I think it's a passage relating to that handwritten table I showed you. So the systematization of problems in the papyrus, and what does not show up on the screen at all. Pete has sort of highlighted this paragraph, and he's written, "But why?" And that's the sort of thing that's appears throughout. He just sort of doesn't necessarily agree with Neugebauer. He just doesn't like the force with which these ideas are put across. Which is not to say that Pete is completely happy with what people are writing on ancient Egyptian mathematics. So elsewhere, he does seem to get quite frustrated. So he's 1930, he's just published a short article on a point in Egyptian geometry. And so this article has brought me in a crop of correspondence with the mathematicians, which I could really well spare. And they get more abstruse every time. And I think he's talking about this kind of mathematical speculation where people are just sort of looking at what's on the page and sort of running with it with a sort of slightly modern problem-solving kind of mathematical mindset. So a couple of names that I haven't mentioned. So Struve was a Russian Egyptologist. Chase is the person who produced this later edition of the Rhine Papyrus. They come in for some criticism in other letters, because if there's one thing that Pete couldn't abide, it was sloppy scholarship, and they were guilty of that in some respects. But Pete certainly, aside from what people are doing with mathematics, Pete always puts the language first. I really like this quote when he's reviewing one of these mathematical works on the structure of this table in the Rhine Papyrus, and notes that there exists a science of paleography before which even mathematics must sometimes bow. So not necessarily a view that is going to find favor with mathematicians, but he's he's nailing his colors to the mast here. And there's a possibly because he's somebody who's taken this meandering route through his career, and now he's presenting himself very much as the philologist. So he's definitely going to go with the philology at this point. Okay, so how many minutes do I have left now? 3. I can do this. So I'm just going to finish off with a few comments about a different text. So the Rhine Mathematical Papyrus it was the first text that was found on the mathematics of this period. It remains the best by a very long way. It's complete. It's not as heavily damaged as some others. The second best one that we have is the Moscow Mathematical Papyrus, which is in the Moscow Museum of Fine Arts. It was bought from a dealer by a Russian Egyptologist called Galenishev in the 1890s. It eventually finds its way into the museum. And people in the West know that it's there for a very long time. But it's only as you get into the mid-1920s that people actually are starting to get some sense of what's in it. And it largely corresponds to what's in the Rhine Papyrus, but with a couple of extra things. One of those being the problem that is here, which relates to finding the volume of a truncated pyramid. And so Pete, along with a collaborator, writes a paper about this, and they're quite happy to attribute some knowledge of some version of this modern formula to the ancient Egyptian scribe, not in a symbolic form, obviously. But then there's speculation about how this was actually arrived at. And so this again gives another little boost among mathematicians to the study of ancient Egyptian mathematics, because if I were to reduce this whole project to a soundbite, what you tend to see is that when a new source emerges on Egyptian mathematics, the Egyptologists are looking for something new, whereas the mathematicians are looking for the familiar. and this counted as the familiar. And so they were very happy to see a bit of three-dimensional geometry appearing there. The other thing that appears in the Moscow papyrus, and as you can see, it's in a quite heavily damaged portion of the papyrus, relates to a basket, and we're being asked to calculate something in connection with this basket, and we're told something about it. And there's a debate about, is this a hemisphere, or is this are we being told to calculate the curved area of a half cylinder? And so, of course, if it's a hemisphere, then that automatically is something quite a lot more sophisticated than the other mathematics that we've seen, because it's, it's a surface that you can't flatten down onto a plane. And so the mathematicians almost universally are very keen to have that interpretation appear. Pete is somebody who argues the other way, and makes the point, of course, that we can never actually be certain at all, because the papyrus is just too damaged at the crucial points. So we can never know. So he gives this very careful argument based on language as to why it should be the curved area of a half cylinder, and notes that I do not know how many mathematicians I shall convince of this, but I'm persuaded that no philologist will doubt my restoration of the data of the problem. And then he really hits the nail on the head by commenting, the reasons which might incline us to the one solution or to the other are psychological rather than rational. So people will see what they want to see in the text. Okay, so to conclude, this is my final slide. Beginning of the 1930s, Pete gives a lecture at the Rylands Library in Manchester for a general audience, so a very general talk about ancient Egyptian mathematics, because he's the authority at this stage. And one of the interesting things he does in that talk is he divides the study of ancient Egyptian mathematics into two phases. So he says the first stage consists in examining and describing the actual processes used by the Egyptian mathematician. So this phase is where Eisenlohr belongs, so actually unpicking the mathematics. In the second phase, we attempt to analyze the mental processes which underlie the actual operations. And so to this phase, both Pete and Neugebauer belong, and yet they're approaching it in very different ways, but somehow they still both belong to this phase. But then if we sort of go with this view of how things developed, there's a very natural consequence of this second stage. So there are very few sources, so you quickly exhaust them. And if you are a cautious Egyptologist like Pete and you don't want to speculate much beyond the sources, then there's not very far to go. So you quickly run out of things to do. And so the Egyptologists sort of don't really say very much more about ancient Egyptian mathematics after this point. People like Neugebauer don't either, because they sort of exhausted the mathematical interest of these sources. Neugebauer, for one, moves on to Mesopotamian things for greater interest. And so, and also I should mention, Pete died quite young as well. So as this sort of person promoting the study of ancient Egyptian mathematics, he sort of disappears from the scene in the early 1930s. And so the Egyptologists are no longer looking at the mathematics, and the historians of mathematics like Neugebauer are no longer looking at the mathematics. So it does sort of seem to end up in the hands of mathematicians. So people who are relying on second or third hand interpretations of the original sources. And of course, then there's this sort of great sense of ownership of the history of the subject, the pride in the antiquity of the discipline, but always with this slight hint of doublethink, where it's not interesting mathematics, but it's there. And that's what matters. And then just to conclude, of course, it's only in the 1990s when you have people like Annette Imhausen and Jim Ritter who are starting to sort of look at ancient Egyptian mathematics again in this more contextualized way. But what I find quite nice to see when you sort of read that work is they're saying things that basically Pete was saying in the 1920s, but nobody was really listening to him at that time. That's a slightly more somber note than I was intending to finish with, but I will stop there.
Thank you for the tour. And we've got time for questions.
is there also a new interest among Egyptology in mathematics, in history of in ancient mathematics? Because I remember that there's a guy who's taking care of the Carlsberg papyrus in Copenhagen, and now I've forgotten, it's embarrassing how to remember his name. But he's very interested in reading these texts when they find a new text in the desert, he said, with mathematics in them. And they are apparently quite interested in studying mathematics there in Egyptology.
Okay, but I'm interested to hear that, because in my experience, oh, is that gone again? In my experience, no, the Egyptologists are really not taking very much interest in renewing an interest in the mathematics. But the ones in Oxford aren't anyway. Let's put it that way. But yeah, it's nice to hear that there's others.
About interactions between Egyptians and Babylonians, say,
Very little. Very little concrete anyway. So this again is somewhere where you find, and I'm just taking sort of Pete and Neugebauer as representatives of two very broadly painted groups of people, but I think Neugebauer looks at the mathematics and says, well, that bit of mathematics in Mesopotamia looks like that bit of mathematics in Egypt, so there's some connection there, even if there's no provable link. Whereas Pete is less willing to do that, and I think there is evidence of connection in a much later period, but I think at this period it's a bit, maybe they did, maybe they didn't, but you know, the evidence is not there. I don't think so, as far as I can remember. No, that's somehow quite different. Maybe there's a 3, 4, 5 triangle somewhere, but apart from that, I don't think there's any evidence that people were thinking in that way, really.
I've got a kind of impossible question.
Okay.
You've shown us 2 papyri. Is there any speculation if these are unique, or if there would have been very many of these at the time that we just don't have, or if there's any sense of how these fit into a larger intellectual tradition?
It's not clear. So the Rhine papyrus probably came out of a tomb. So anybody's best guess is that this is very definitely a sort of, this is grave goods. This is a neatly written scroll that goes into the tomb that the scribe, this must be a high status scribe, could take into the afterlife and show his skills. And so what relation that has to what he was actually doing in his working life is not clear. That there are a couple of can't think of the name, writing boards that have, you know, wooden boards with arithmetic on them, which are probably more representative, slightly earlier period than the Rhine papyrus, but a similar kind of mathematics. So the Rhine papyrus probably reflects what people are actually doing, but in a sort of neatly written up form. In a way, the Moscow papyrus might be more representative still, because it's a mess. I can't remember what word Pete uses. He's very English about it. I can't remember. It's atrocious, or something like that is what how he describes the writing on the Moscow papyrus. So yeah, so that could be more representative.
Maybe it is too much to ask, but if you could give us an idea of which were the main criticisms that Rita and Una also raised days, not an hour, well, so it's a bit too much to ask, but would be grateful if you could just give us, general outline of the recent 1990s, post-1990s, of interpretation.
Yeah, so it's embedding the text much more in a wider cultural context. So, for example, doing more with economic texts that were not, they're somehow not strictly mathematical, so they get left out by Neugebauer. So it's sort of bringing in more texts of that kind. It's trying to place things in a context, which is quite difficult when these things don't have an archaeological context. So I'm thinking a little bit more of the things that have been written about Neugebauer in his work on Mesopotamian mathematics. So here it's the very sort of internal view of a text rather than thinking about where it sits in a society, and also I think so Jim and Annette have this view of a much more sort of algorithmic approach to what's happening in the text. It's sort of method based. So they're drawing parallels there between the mathematical texts and the medical texts, which is kind of, you are told this, therefore you do this, and then you do this, and then this happens. And so there's a similar structure there. And that's the sort of thing that, again, Neugebauer is looking at maths and astronomy. He's not looking at the medical texts. So sort of bringing in things where there are parallels that you wouldn't necessarily look for if you were focusing very much on mathematics, I suppose.
I'm happy to chat further over tea or next week if you're around.
Sure.
But
Yeah.
For now, we will thank you again for your participation. And we'll convene on Monday morning.
We will.
Program starts.